everyone is, out of Tijuana prisons and stuff like that. Have too much fun in Juarez. Awesome. So we have roughly 4 weeks to go. We can put a bow on this thing, and we will be good. I got through all but 5 of the reports. In general, they were pretty good. I would say of the stuff that I was griping about on the reviews, your experiment was over. So your report should have been in the past tense. You should have told me about what you did. And a lot of you guys framed it as, especially in the procedure, you said, go do this, go do that. Like you were telling next year's class what to do. Not really the deal, guys, okay? That's why I said it should be in the past tense. You're reporting your results. I didn't get crazy taking off points over that, but you remind me to be more emphatic next year, or whatever this class turns into next year. So that was it. The other thing is, with technical writing, okay, it's not an informal thing. I saw a lot of colloquial expressions, stuff like that. We aim to prove this. No. So I did a lot of wordsmithing, marked it up and read it, sent it back to you. The intention of this experiment is to blah, blah, blah. Okay. But in general, they were pretty good. Most everybody was 80 plus. You will have a chance to rewrite your reports to get a better grade. If you just plain knock it out of the park, which a couple of you did, if you got a 94, 96, and you're like, I got better things to do, and I've already got an email down to the class, just send me an email and say, we're not going to resubmit, give us the final grade, and I'll just put in, whatever you got on your report grade, I'll put that in as a second rewrite. Done, you can walk away, call the class good. Just take the A and move on. Okay, so that's all the business stuff today. Pressure sensing. Okay, there are a gazillion ways to sense pressure, folks. We're going to go through some of the really basic ones. To start off with, we need to talk about the different pressures. You've got absolute. So what is the pressure relative to a vacuum? You've got gauge pressure. What's the difference between whatever I'm reading and my current atmospheric pressure? And that kind of gets into the same thing as differential. So for example, manometer, probably one of the most basic pressure sensing tools you could probably have. You put some water in it, you get 2 different heights. The difference in height is actually your pressure. There's a lot of things in this world that use pressures in like inches of water. When I was an intern, I worked at a company that made kitchen equipment. All of our gas lines were all running 10 inches of water column. So I actually had a manometer just like this when I was tuning the fuel manifolds on a McDonald's French fry machines. So you will run into this. So if I wanted to do this as gauge pressure, maybe I'm just going to blow into this thing. I'll leave the other side open, and I'll measure the height difference between the 2 water columns. If I've got 2 different sources of pressure and I want to measure it as differential, I could take and hook up one side here, one source of pressure, hook this side up to the other source of pressure, and I could measure the difference in those 2 pressures by measuring the water column height. Moving along. So in the old days, when we were just starting to measure pressures in like the 1600s, we had this guy, Evangelista Torricelli, and he measured atmospheric pressure by having atmospheric pressure pushed down on a bowl of mercury. They didn't have ocean in those days. And that would cause the column of mercury to move up and down. Okay? That's your barometer. Basic sensing. Moving forward a couple hundred years, we have the Borden gauge. Just what this thing is. Simple, cheap, easy mechanical pressure gauge. That little C-shaped ring up there, okay, when that thing inflates, it wants to straighten out, and it moves. And that drags the linkage with the rack gear. The rack gear moves the little pinion gear, and that changes the dial, and that's how it senses pressure. So it's strictly a mechanical thing. But you can still get them at Home Depot, and they're pretty cheap, and they work well if you don't need to talk to any other equipment. Yeah, so yeah, you can put strain gauges in them, you can get electronic output. Not that common. Okay, if we want to jump ahead to the 1970s, and maybe we want to look at, the oil pressure sender in our 72 Mustang or something like that, you'd have something like this. You'd have pressure coming in, the Borden tube unravels as the pressure increases. You hope you have oil pressure, otherwise things will go bad quickly. And that was turning a variable resistor, and that's how you got your electronic readout, and that was what was driving your oil pressure gauge on the dash. Thank goodness those days are over. I mean, the 70s were cool and all, but no. Moving along to something a little more modern, you've got this little gizwizzing. This thing is basically just a closed pipe with a full bridge set of strain gauges on it. And as the pressure goes in, it deflects the diaphragm, the strain gauge is strained, and you get a pressure readout. Okay, just like that. Okay, this one is really, really nice because it has 3 wires. So in this particular model, I put in 5 volts, I hook it to ground for power, and inside here is the amplifier, that INA 125P or some equivalent to that. And that amplifies the output of the bridge. And then on the 3rd wire, I believe it's the green wire, I'll get some analog voltage that's proportional to the output. These things are nice in that they have kind of an error tracking involved. This thing runs on 5 volts, so if I have 0 pressure, like right now, I'm going to get half a volt of output. If I put this thing all the way up at its full rated 30 psi, I'm going to get 4.5 volts out. So I've got a 4 volt swing in there that's between 0 and the rated pressure, and it's linear. So these things are very, very nice because they're easy to work with, and they're very durable. You can get these things in anything from, this one is -1 atmosphere to 2 atmospheres. I've got some 1,500 and 2,500 psi over in Crosby. And all it is just a change in the diaphragm thickness. If you want something a little cooler, you could try doing pressure sensing with just capacitance. So I could have my diaphragm up there, and as the pressure changes, I could change the gap. So we remember from our electrical course that a capacitor is just 2 plates, 2 conductive plates, separated by an air gap. Occasionally there's a dielectric in between to amplify the capacitance. Okay. Maybe, maybe not. But as long as that gap is changing, I get a change in capacitance that's proportional to my pressure. I personally haven't run into those, but they are out there. So you're going to need some a little bit fancier electronics to deal with those. Here's an example of one. This little one I've got, this was 18 bucks. That capacitive one, $1,400 in 2018. Okay, it's there if you need it. Let's say you want to measure some really sensitive pressure variations, like maybe Beyonce's voice. Okay? That's all a microphone is, guys. That's an electret microphone. And I actually worked down in Camden at a place called Tibbetts Industries, and we would freeze electrons into a sheet of Teflon. And this still hurts my head to this day. But this is what we would do. We would freeze electrons into Teflon, creating a permanent charge, and then as the diaphragm in the speaker moves back and forth due to sound pressure waves, you would get a voltage change because the diaphragm is moving closer or further from those frozen electrons on the Teflon. Okay, I still think aliens came up with that, but they don't let me go to Area 51 and check it out. So I'll just say, probably human invented. Okay, but if you need to measure very small, highly dynamic pressure pulses, something like the electret microphone is an option. This is one of the ones that I played with. Teeny tiny little things. We used it for all kinds of stuff. We used them for detecting Russian tunneling under embassies. We got into some other interesting applications of sound. So, unfortunately, that company doesn't exist anymore. They were bought out. As we get smaller and lighter, you get more into the micro machines technology, or MEMS. Okay, so you can buy pressure sensors that go right on the circuit board. That thing will plug right into an 8-pin socket, and you can have a little capillary tube going right over to your pressure sensor. Okay, again, 18 bucks. It's got the diaphragm, the amplifier, all that good stuff built right into it. And the last one I'm going to go into before we do a little experiment. Piezo pressure sensors. Okay, let's say you want to measure some really big, really dynamic pressures. Okay, that thing right there, that's an M1 Garand. That was the rifle that the Allies carried when we invaded Guadalcanal. When I pulled the trigger on mine, for about 1 microsecond, there's about a 60,000 psi pressure surge in that barrel. Okay. So if I wanted to measure the pressure that's cycling the action on an M1 Garand, and I tried putting this little thing in there, no, it's not going to go well. This is neither fast enough nor will it take enough pressure. This diaphragm would just blow apart, and probably I'd have guts of this thing skittering across my front lawn. Because, that's where the age-old saying, get off my lawn. Okay, but think about piezo. You gotta remember. So if you're not familiar with piezoelectrics, they are a material that creates an electric charge when they're deformed. Okay? And they're proportional to thickness. So you can have very thin piezoelectrics that will actually wag back and forth when you put a charge on them. If you have thicker ones, you can get more force, but smaller deflections. So that is how the piezo works. And the thing about it is, let's say that I deflect the diaphragm in this little guy. Okay, it imbalances a Wheatstone bridge, and there's a constant signal. Okay. That piezo, that if you deflect it and you stop the rate of strain, there's no signal. Okay. That's what's tricky about those. So if you want to use them to get pressure, you must do a very fast time integral of the rate of change. So that's got to be built into your controller to use a piezo pressure sensing system. So just be aware of that if you ever come across these things. Because you might see, okay, I have a change in pressure, boom, I've got a signal spike and then it goes to zero. It goes the other way, I've got a negative pressure signal and it goes to zero. And you'd be going, what happens? Well, what's happening is you didn't do the time interval to actually get back to a pressure. Okay, and this is actually the M1 Duran's pressure profile. So at about 500 microseconds, the pressure in the gas system is up around 1100 psi. That's actually a lot less than I thought. Chamber pressure is 60,000, but the gas system's a lot less. Probably because the gas port's down at the end of the barrel. So that gas has already had a chance to expand. But I'll save you the lesson in rifle dynamics. Okay, enough of the slides. So, experiment of the day over here. I think that every student, before they get out of college, should see this little experiment. So what we're going to do today is we're going to put some water in that jar, and we're going to pull a vacuum around it. And inside here, I've got a little, got the thermistor. So we're going to watch what happens to the temperature of that water as I drop the pressure. So let's just do it once. We'll do it once just to see what happens. And then we'll do it actually watching the temperature. The cool factor in this comes from actually getting a really good vacuum. If you have any little break, the cool factor goes down. No science is worth doing unless it has cool factor. I should be using vacuum grease, something with a very high vapor pressure. But unfortunately, this is all I can come up with on short notice. And just kind of rotating this around, just trying to establish a nice black appearance all the way around so they don't have any gaps. Get it most of the way. So here, and so right now I've got the vent valve opened, and we'll flip it on. Amazing! It needs electricity. always practice any demonstration. Good, sir. Thank you. All right, let's try it now. So I'm going to close the valve. There. Okay, my question to you guys, what just happened? What happened to the temperature of the liquid? I think we should data log it and actually watch the temperature profile. Take that off. Wipe out the vapor. I missed it. Put the temperature sensor in. And we're going to do the exact same thing all over again. Only this time. So you got to see it once. We drop the pressure, it starts to boil. Now we're going to come over here. Now we're talking, we're exchanging data. And my water's at, give or take 109 degrees F. And we'll close the valve and start dropping the pressure again. I added a little too much water. And I clearly have another vacuum loop. pull it down to 0.2 pascals. That's way low, folks. Way, way low. Okay, so my water go from 109 F down to about 83. Even despite my obvious air leak. What just happened? You want another shot at it? Okay, and this is exactly why I think everybody should see this demonstration before you get out of this place. So what happened was, at 109 degrees, you got a certain saturated vapor pressure on top of that water. I lowered the ambient pressure below that saturated vapor pressure. When the ambient pressure goes below the saturation pressure, it boils. That's what it does. So in the boiling process, because I do not have heat, what it did is it traded its sensible heat, you know, that MCP delta T, for the phase change. So basically, by changing the water to steam through lowering the pressure, I dropped the temperature. And pilots really worry about that. There's this thing called the Armstrong limit. So if I'm Joe Cool, fighter pilot, and I'm flying my MiG-25 Foxbat, and I want to go up to, you know, I think it's like 90,000 feet, at some point, I hit the saturation pressure where it's 98.6, and my blood starts to boil. It's called the Armstrong limit. So, I hope you guys understand that we've just done boiling. We've traded sensible heat for heat of vaporization. That drove the temperature down. And the more I pull saturated vapor out of this thing, the lower and lower that temperature is going to go. So someday I hope one of you guys will be really cool and make a non-CFC, non-refrigerant, non-ozone depleting air conditioning system with just water. So we could have gone from a very uncomfortable 110 degree room, well, now we're down to 80, and we're still dropping. So you can absolutely use water as a refrigerant. All right. And it will just keep going. If I had worked a little harder and got every last leak out of this, and we did in fact go down to 0.2 pascals, we would have ice in that beaker. It would go all the way down. So let's imagine we want to know what the pressure is in there. Let's say that we're going to say, okay, fine, 80 degrees Fahrenheit. Use engineers school bars. So let's see, at 80 F, I'll be right about here. I'll come up to my saturated vapor line. I'll go over. So I'm at about 0.8 PSI in there. So I've got some pretty good leaks going on. That's nowhere near 0.2 pascals. That would put me way down here. Okay, yes, I know that was fast. I know it was not super in-depth. There's all kinds of pressure sensing technologies out there, folks. Basically, if you can find one that's a simple Wheatstone bridge diaphragm type, these are super easy to use. Unless you've got some freaky speeds and pressures, look at these first, and I will see you next week. Thanks, guys.